can introduce the first speaker of this afternoon session, Cristoforo Iossa, you may know, who will be talking us about where and when large charge meets semiclassics in unequal force superior means.
Okay, thank you for the introduction, and I want to start as usual by thanking the organizer for this wonderful workshop in this very nice location. Okay, so today I'm going to talk about large charge and semiclassics in unequal force superior meals, and this is going to be largely based on these two papers that came out recently. So the first one is in collaboration with Alba Grassi, and the second one with Alba Grassi and Zonka Wen, Gus Brown, and Francesco Galvagno. So the main motivation that, like my personal motivation for studying this, for studying this topic, is that I wanted to study a bit like correlation functions involving heavy operators in some holographic theories. So in general, this would involve, so if you want like the final goal, very like long-term goal would be to study correlation functions of like n equal 4 superior meals with SUN as a gauge group. And by heavy operator, typically it's meant operators with a, so this is a CFT, so we would like to consider operators with a scaling dimension that scales like n or n square. Then typically we keep fixed the so-called top coupling, which is Gn mil square times n, and we send n to infinity. So these are very important objects, as we also learned this morning from Rodolfo's talk. They sometimes can be studied from like some bulk geometries, considering some fluctuations of some bulk geometries. But the idea would be to study them from a boundary perspective, so only like looking at the CFT. We are not there yet, so we will consider.
You are also planar, as far as I can understand.
Yes. So we are not there yet. So where we are at is in some, if you want, somehow simplified version of this. So we managed to consider, as I will discuss, SUN as a gauge group. But instead of considering heavy operators that scale with n square, I will just consider operator whose dimension scales with some charge, small n, that we are going to take large. And instead of considering the usual top limit, we will consider this, if you want, a larger top coupling in which Gn mil squared times the charge n is kept fixed, and this small n goes to infinity. So I will not say much about some possible holographic interpretations of this, but a way in which you can think of like connection between these two regimes is in which this parameter alpha is much larger than 1, so delta becomes the largest parameter in the game. So the tool that I will use to study this kind of objects is through some semiclassical analysis. And before going into the details of n equal 4, I wanted just to mention that studying semiclassical, like studying large charge correlation function, so correlation function with large charge operators in QFT is a very old story, actually. I think that the first time something like this appeared was in a paper by Rubenkov in 95. And a bit after that, I think a paper by Son in 97, if I'm not mistaken. So the motivation of this paper was, so what they wanted to do, they wanted to study correlation function that involved a very large number of external legs, of external particles. And this is like, I think that the motivation is that this is somehow a realistic thing that could happen in some collider experiment in which you have a large number of particles coming out. So they noticed that something funny indeed happens from a semiclassical point of view if you study correlation function of this kind. So I think they considered like phi to the 4 in 4 dimensions. I'm going to call the coupling G because lambda is going to be this. So this is a U1 symmetry, a global U1 symmetry that rotates the complex scalar. So the scalar is charge 1. The simplest way that you can consider to make something heavy is to consider the composite operator phi to the n. Now this will have large n, and you can send n to infinity. So they wanted to study like renormalization of this kind of operators. So a way to do this is to consider correlation functions, which you put one of these composite operators, and then a large number, precisely n of them, of light guys to saturate the U1 charge. So the canonical way to compute this is just by a path integral analysis. So we get the measure, we insert our composite operator, all the light operators as well, and we have the classical action. So typically what one does is just solve for the saddle point equation, delta S, so that like variation of the action is equal to 0. This gives you some vacuum, and then you can expand in fluctuation of this vacuum. So this corresponds basically to like the usual Feynman diagram expansion. However, something funny happens, because already at one loop level, you will get something, maybe, you get some diagrams like this. So you have n minus 2 legs here, and then 2 legs that contributes with a quartic vertex. And you can convince yourself that this when n gets very large, this scales like g, coming from the quartic vertex, and n, when n is the charge. So when n is very large, this breaks down. In particular, you can consider n of being like 1 over g, and this will be of order 1. It gets worse than this, because you can see that you can convince yourself at least that if you consider L loops, so L loops diagrams, you will get something of this form. So this is also of order 1 if you set n to be 1 over g. So all the loop expansion resums at 3 level already. So this is a signal that perturbation theory is breaking down. And when this happens, it typically means, or it can mean that we are expanding around the wrong semi-classical saddle. So what we did wrong here is that we consider the variation of the action to be 0, but we don't have to do this actually, because when we do this, the perturbative expansion that results from here breaks down. What we have to do is we have to include sources, meaning that the heavy operator enters the saddle point equation and sources the usual vacuum. So it modifies the vacuum, then you can compute fluctuation around this vacuum, and this will give you some well-defined perturbative expansion that does not that is well-defined. So this was in the context of so this was 5 to the 4th. I just wanted to mention that this, for example, has also been extensively studied in the context of the Wilson-Fisher fixed point, and there is in particular a paper that I want to mention by Cuomo, Rattazzi, Badel, and Monin, that was called the epsilon expansion with semiclassics, and I want to cite it because we stole the title from there. So it was, I thought it was worth citing. Okay. So this is the general setting, and basically this is the very simple idea that will underline all of the talk. We have to find the correct semiclassical saddle that we have to expand around so that we get a well-defined perturbative expansion. So the plan of the talk will be the following. Maybe I can write it here. Sorry? Are you thinking about n-point functions? Most of the talk I will talk about 3 or 4 point functions, or 2, where 2 of the guys are heavy. But in principle, you can consider higher point functions as well. So the plan of the talk will be the following. So as I mentioned, I want to discuss n equal 4 Superman Mills. So in the first part, I will simply review what happens for the simplest possible gauge group, which is SU2. And this has been extensively studied in a nice paper by Joao Caetano, Shota Komatsu, and Yifan Wang. So I will briefly review a section of this paper, and then I will move to the case to our main results, which is an extension to SUN. So in the motivation, I said that we want to kind of get close to some holographic limit, so I will discuss some comments at large n. like what happens in large n. We didn't treat this in, like, we didn't study this in detail in the paper, but I just wanted to show you that some general feature, what is expected to happen in large n theories, will also show up in this case. Okay. So in the first part, as I was mentioning, I want to review the SU2 story, and in particular, I want to set a bit the notation. So we have to find some heavy operators in n equal 4 superior mills, and as it is well known, the heaviest part of the spectrum of n equal 4 is like very, very complicated, even for SU2. So we will simplify our life a lot, and we will just consider half BPS heavy operators. So heavy operators will be always half BPS. In n equal to 4, we have three complex scalars, x, y, and z. They correspond to the three U1s in the Cartan of, so U1 that I'm going to call them U1x, U1y, and UZY1. And they are the three Cartan in the SO6 R symmetry group. Now, half BPS operators are made up can be constructed taking traces that are only made up of a single letters. So, for example, you can consider traces of Z's, and this will be all half BPS. So these traces are over the gauge group. The gauge group is simply SU2. So basically, the only non-trivial single trace operator is trace of Z square. In fact, if you consider trace of like Z cube is 0, Z fourth is D squared, so this is the only independent trace that you can consider. This will have R charge 2, and this is also like, there is some proportionality factor that I don't remember, it's 2 or 1/2, but the R charge is 2. So the basically only way, keeping only Z that we can consider to make up a large charge operator is simply considering trace of Z squared to the n. And again, the plan will be sending n to infinity. I'm going to call this OH, is our heavy operator. And I want to work, as I mentioned in the beginning, in the limit in which we consider GM is going to 0, such that as n goes to infinity, n times GM is squared is fixed. So this is fixed. So this is not the usual Toft coupling, where big N appears there. Okay, so this is the general settings. These are our heavy operators, and the goal is to compute correlation functions of this form. So we have OH bar. So actually, so this is at x1, this is x2, and then we can consider, in principle, as many light guys as we want. So I want to mention that we said that this has to be half BPS. So this is this. But the light guys can be whatever. In fact, in this paper, they computed like a 3-point function with Konishi, which is 0 BPS. So light guys can be generic in principle. Now, again, the idea, the way in which we want to compute this correlation function is via a path integral computation. So we have a path integral over all the n equal 4 fields. Here we have all the light operators. And then we have the n equal 4 action completed with Gauss, gauge fixing, and whatever. And I'm going to normalize everything such that I can write down a GM mill square overall here. So here I have n equal to 4. And then what we want to do, as I mentioned in the introduction, is that we want to put the sources in the exponent. So when we exponentiate this is e to the n log trace, but n is lambda over GM mill square. So this is simply lambda log trace z square plus the complex conjugate. So this is our path integral. And you can see that with this nice normalization, the sources contribute to the same order of the classical action, so it would be completely unjustified to like treat this as perturbations of the saddle point. So they really appear in the saddle point equation. Okay. Sure. Mm-hmm. Sorry? I think it's easier to study this the situation in which you have two heavy operators from the perspective that we are taking anyways. Thanks.
In Rajan, can you explore some techniques due to when story that the theory somehow has some integrability structures?
We didn't explore this, but it would be nice, I think.
Because a fixed n would be a rather different picture.
These are always very heavy operators, so even larger, you want to take the dimension to be of n, and I think that's outside of the integrability limit. The integrability limit is 4 because of dimension much smaller than n, such that you can concentrate on serial traces and multiplexes. Like, for example, here n is much larger than, like small n is much larger than large n, which is just 2, and even with large n, you would want to concentrate.
It depends a little bit on the order of limits, actually.
Yes, but I think that the original motivation was for dimensions.
Yeah, but okay, but we didn't consider it for the moment, so it... Sure.
The source is evaluated at some point, is not integrated.
Right? Yes. It's evaluated at x1 and x2. Okay. So, sorry? Yes, that's actually a good, this is actually, there is, oh yes. It's not the complex conjugate, it's trace of z bar square at x2. And this is gonna show up at some point. Okay, so the saddle point equation we have to solve now has to include sources. So the variation takes this form. We have lambda log trace of z square plus log trace z bar square equals 0. Okay. No, they are evaluated at the
So they could come out of the
Oh, well, you integrate, like the field is integrated, but the insertion point stays. So there is a delta function if you want at the insertion point. Okay. So this is the saddle point equation we have to study. So in principle, the way to do this is to take the action, expand it in terms of like all the fundamental fields in the gauge matrices, expand the traces, expand everything, and solve the differential equation that comes out of it. Turns out we don't have to do any of this, and the reason is simple. So let me call by Z classical the solution of this equation. So first of all, it's quite. So we can immediately see that the only scalar field that will acquire a non-trivial configuration is the Z field, because everything is happening along the Z symmetry direction. So we are only looking for some non-trivial thing happening to Z, and we can always put Z in diagonal form up to gauge transformation. Now our goal is to find Z0, but this is easy. And the reason is that S does not depend on lambda, and it depends quadratically at Wheeling order on the field. So this has to scale with square root lambda. Then this is basically a 3-point function in a CFT, because this is like O heavy, Z, O heavy. So the space-time dependence is simply fixed by conformal symmetry, and this is going to be something like x1 minus x2, x minus x1, something like this. And then everything depends on the square on the modulus square of z. So we will get a phase. So this phase is a modulus of the solution of our saddle point equation, and it has to be integrated over. So let me mention that, for example, if we consider, so this is important because, for example, if we consider generic, so if we consider generic theta, this vacuum is is Xing the gauge group down to U1. So we have SU2 is broken to U1. But if you consider, when you consider the integral over theta, this is integral of e to the I theta, and this is 0. So after the integration over theta, the gauge symmetry is actually restored. So there is no breaking. So the theta parameter is a modulus, and we need to integrate it over at the end. But before doing that, we can really think that this is breaking SU2 down to U1. Okay, so what we did is that we found the saddle point solution. What we have to do now is to consider the fluctuations around the saddle point. So for generic theta, again, the gauge group is broken, so fluctuations, so the fluctuation that commute with the breaking matrix will stay massless. But fluctuations like the off-diagonal fluctuations will get a mass that is space-time dependent. So if you want, it's a potential. So the Lagrangian will contain something like z0 of x squared times off-diagonal fluctuations. So this means that the propagator of off-diagonal fluctuation is non-trivial, and I'm gonna call this t. And the way to get t is simply to find solve so invert the kinetic term. So t is a solution of z0 x, t of xy. This is equal to delta of x minus y. Note that z0 square depends on lambda, so t is gonna depend on lambda. So this is gonna contain all the, at 3 level in this semiclassics, this is gonna contain all the lambda dependence. So this equation seems a bit complicated, and indeed it is a bit complicated, but it has been luckily solved explicitly. By Jombie and Hyman, sorry. So this has been solved explicitly, so you can solve it perturbatively in lambda, and this is I'm not gonna write formula for this, but this is just given as a series of the logarithm or something like this. Turns out you can also resum the lambda dependence in this case, so you can evaluate this at finite lambda. Once you have the propagator for the massless scalars, for the massive scalars, and the propagator of the massless ones is of course the usual free one, then you can evaluate. Oops. Then you can evaluate these correlation functions simply by integrating all the light fields. So considering correlation function of all the light fields in this theta vacuum, and finally integrating over theta. So again, as for generic theta gauge symmetry is fixed, this means that in order to compute this correlation function, we really need to open up gauge matrices and consider all different weak contractions that involve this non-trivial propagator. But in principle, this can be done, and in fact, it has been done in this paper in some detail. Okay. So this is what I wanted to say about SU2. If you have no question, I'm going to move to the SUN case.
because this explicit result is for how many line operators?
So what they did in the paper, and this is also what we did for SUN, is for two operators in which you can and the operators are trace x squared basically. So this is like the things that you would get also from integrated correlators perspective. They also computed the 3-point function with the Konishi, and they got some explicit result that depends on lambda and can be evaluated at finite lambda.
So 2 half BPS or 1 Konishi?
Yes. Which is roughly the same because when you p things you can get, but it's
2 Konishi has not been done.
No, but you can, like in principle there is no difficulty because at this point, so that doesn't really change too much if it's at 3 level in this expansion, it doesn't really change much. You just have to expand everything. Yes. No, it's just a phase. Because it's just because everything depends on z0, z0 bar. So you get. Okay. So this was SU2.
If instead of that space, we would have thought about states on the cylinder, then I would have expected that the 3 factor, which was something like x12 divided by absolute value of x12 squared, or something like that, to just be dropped off.
Yes, that's what happens indeed.
But then it seems like the state is not charged because you have nothing that's time dependent. Maybe I'm missing something.
The reason is because the coefficient in front of that pattern with the low price is rated to FT. So the user case of that charge and all real operators, so that create the operator is real, these are charged, so they define a coefficient. So it doesn't basically change. No, this is not related to the one of the this is like a phase ambiguity in the FT.
Yeah. Sorry, maybe I should have mentioned this before. Okay, since this is everything half BPS, dimensions are protected. Everything is so the dimension is always equal to n. There is no numerous dimension going on. Okay.
Maybe you mentioned, but why did you have to take lambda charge to do the derivation?
It's just that if you don't take large charge, then it's like you cannot really compare the action to the source. So if you take, for example, n equal to 200, then of course, like it should be well approximated by this. But if you take n equal to 200, then like if you want to, like 1 over g square is always much bigger than 200. So you would get something in the loop expansion. You would get something like g square 200, and this is if you want parametrically small. Maybe not numerically, but parametrically small. Okay. So let's move to SUN.
Sorry, Cristoforo. Yes, the very fact that the given function is exact, in the sense that it's telling you that if you would apply the semiclassics totally saturated by its classical value. Right?
Sorry, the 2-point function is exact, you mean? Yes.
Which you see there are no corrections. So,
yes.
So I believe that all the other correlators like the operators are just exact. There are no corrections.
No, because so what is exact? So this is exact. It's 3-level exact. So and this is this you would get by doing the semiclassic and plugging back the thing in the action, and like you get a number, and that's what it is. If you want, this is coupling independent. But now when you consider, for example, sorry? Yes. They are. But for example, when you consider a 4-point function like this and you OP them, you get Konishi. So you can see immediately that this gets corrections. So the 2-point function is indeed the 3-level exact, but 4-point function is not. Okay. 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 So SUN. Now in SUN, we want to do basically the same thing. So again, OH, we want it to be half BPS. Again, we have X, Y, Z, asymmetry, blah, 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 and half BPS things are traces of a single letter. There is a large complication that arises now, a big complication, that is the fact that while for SU2 we only had trace of Z squares, now we have n-1 independent traces.
Cristoforo, you are around half of your cell.
Okay, thank you. Yeah, it's okay. So we get from 2 to n. So this is just like the fact that for SUN you have many linearly independent traces. But there is another thing that happens for SUN, that if you consider SU2, there is only one way in which you can mix the gauge group with an adjoint matrix, that is breaking it down to U1. But if you consider SUN, then you can break it in many different ways that are given by, if I'm not mistaken, should be this. And they should also be n-1. So a natural question that comes to the mind at this point is whether there is a correspondence between heavy, like large charge single trace operators and symmetry breaking patterns. If we can find some kind of correspondence. So one would say, okay, as we did for SU2, we just like plug everything into the action, expand, solve, and it's done. But this is very, very difficult in the case of SUN, because as I mentioned before, you really have to open up the gauge matrices, and when n is not 2, this is difficult. Even for n equal 3, this is very annoying. So we decided to opt for a different, to go for a different strategy. Let me just mention that all the consideration about what the classical value of Z should be also apply in this case. So the solution of the saddle point equation again must scale with square root lambda. Again, the space-time dependence must be this one. But then, okay, again we have a phase, this is a modulus. But then we can multiply this by some like SUN matrix omega. This is SUN. And this is basically the only unknown in the solution of the saddle point equation. So this is what we should fix by explicit computation, but explicit computation are hard. So we found some sketchier but easier way. So the strategy is the following. So the first step is to consider a particular kind of correlation function. So we consider the so-called integrated correlator. So OH bar, say trace of x squared, trace of x bar squared, for example. So this is the 4-point function, and then we integrate it over space-time. It turns out, as it has been found, I believe, for the first time, but I'm not sure, by Binder, Chester, Pufo, and Wang, it turns out that this correlation function, once you integrate over the space-time with a nice enough measure that preserves supersymmetry and blah, 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 can be computed on the sphere, and on the sphere you can use localization. So after you integrate over space-time, this is simply a function of tau and tau bar. This is the unequal 4 coupling. So this you can simply compute by localization. You just go to the sphere, you have all to take care of all the usual details, but you can do it and you have a well-defined way. Now, it will be a function also of small n, right? Yes. It will also be a function of small n. Indeed. So the first part is to just compute it, and like you get what you get. Now we actually do care about space-time dependence of this object, because, for example, the propagator, we want it like with all the dependence. So the second step is to recover space-time. And the way we do this is following a nice procedure that was found by Zonka Wen, Francesco Galvagno, and Gus Brown, in which in the regime that we are precisely the regime that we are considering now, so the regime in which the charge of the heavy guy is very large, such that g squared times n is kept fixed, And in this regime, you can actually recover at leading order in N, you can recover all the space-time dependence of your correlator. So this is the second step, recover space-time dependence, and we can do this in this regime, but this is precisely the regime that we care about. And finally, step 3 is guess omega. So now that we have a bunch of things, like we find a bunch of correlation functions, in this way, we just have to find an omega, so a solution of the saddle point equation that basically works out in all the cases. And then, of course, you need to do all, like, since this is somehow a guessing game, then you need to do all the like non-trivial consistency checks and so on. Okay. So this is the procedure. So you might ask, if you can recover the space-time dependence just by doing what they did, why would you bother? Why would you care about getting the semi-classical thing? And the reason is that this works only for this kind of correlators, these integrated correlators. But if we have the semi-class of the saddle point solution, we can do it for much more general things. We can consider more insertion, the Konishi, and stuff like that. And also we can try to answer the question whether there is some kind of correspondence between heavy operators and Xing patterns. So if you follow step 1, 2, 3 for a generic choice of OH, so OH will be some linear combination of multi-trace operators. Whatever you feed it will give some answer. So if you try to follow step 1, 2, 3 for some generic choice of OH, of course you will never be able to guess anything sensible. So the thing that you have to do is to find a nice basis. And luckily we have some candidate already. We had some candidate because in a paper with a lot of authors, and I don't remember half of them, which were Komarkowski, Pufu, and Korgemsky, I think. They discussed the extremal correlator in n equal 4 and n equal 2. They were doing some localization games, but without entering too much into the detail, they were finding that there is a class of operators that behaves very nicely when you map them to the sphere. So these operators take this form. I'm going to call them O, K, and M. So it's just trace of Z to the K to the M. And then you should add some linear combination of all the others, like multi-trace operators of the same dimension. And this linear combination you get it through a Gram-Schmidt procedure. So what I really mean by behaves nicely is that when you map to the sphere, you have some conformal anomaly. This induces some non-trivial mixing, and you have to mix, blah, blah, blah. And this operator basically takes care of this immediately. So when you consider this kind of operator, you don't have to care about anomalies, mixing. You can just compute them on the sphere directly. So this is a good candidate. And another reason why this is a good candidate is that another reason why we thought that this would be a good candidate is because in this first paper with Alba, we noticed that we studied extensively this kind of objects in the case of SU3. We could find at large charge that there is a matrix model representation, for example, for integrated correlator that involve this object. And this matrix model that we get is very special to this basis. So this really seems like the good thing to work with. So what we did, we tried a bunch of those, and a very nice structure emerged. In particular, we were able to find this matrix omega that takes this very simple form. So let me mention that this Gram-Schmidt procedure it has been done with a very specific ordering of traces. Now I'm not gonna mention it because it's a bit technical, but it's not a generic fact. This is really, you really need to tune the ordering of traces and stuff. So what you get for this matrix is this very simple answer. So this is a diagonal matrix. The first k elements are non-zero, and they are simply the square root of unity. So you have the first k element of the diagonal are the k square root of units, and then you get n minus k zeros. So this is the result of the saddle point equation. And if you look at this matrix for long enough, you can convince yourself that this is precisely implementing the Xing pattern from SUN to UN to the k minus 1 times U to the n minus k. So this OK and M are really one-to-one correspondence with Xing patterns. So this is somehow the answer to the question we were posing before. There is a detail that I should mention at this point, is that this only works if k is bigger or equal than 3. So for k equal to 2, it turns out that these guys are precisely the maximal trace operators, and for some reason that we don't understand really is that this doesn't work for maximal traces. So this only works if k is bigger or equal than 3. But okay, for the SU2 case, it works. K equal to n equal 2 is the only k equal to that works. And for that case, this works precisely in this way. But as soon as n is bigger than 2, k equal 2 doesn't work. You can, like, for localization, the maximal traces are somehow strange, but like not really. But anyway, this doesn't work. Okay.
So does that mean that the large charge for k equal 2 is not known? You know it in another.
Well, you can. So for example, for maximal traces, on one end you can do a lot of many more things. For example, the integrated correlators of maximal traces, literally everything is known, even in the like holographic regime in which delta is n squared.
But for the unintegrated?
But the unintegrated, no, is not known. The procedure of recovery in the space-time that like Zonkao and Francesco and Gas found out, it also works for maximal traces, but in that case you cannot resum the lambda dependence. So it's
difficult to go to the supergravity.
Yes, and also it's difficult. Also, the space-time dependence is you only know it perturbatively in lambda, which is basically a weak up. I mean, it's a bit strange because you would expect the maximal traces are simpler, but so note that in particular k equal 2 would implement the breaking u1 times u to the n minus 2, and this we don't know how to implement, but there was a paper by Shota, Zarimba, and collaborators that find some conjecture that some sure polynomial operators should implement precisely that symmetry path, that Xing pattern. But yeah. Okay, so this is the saddle point equation that we find associated to these operators. So once we have the saddle points, what we have to do again is to study fluctuations on these correlators. So again, this depends on theta. This is only true for generic theta. When you integrate, you recover the full gauge group. But since we can, since we integrate over theta in the end, we can in the meantime work with this under like this Xing. So when we study fluctuations, you can see that all the modes that corresponds to the unbroken gauge group, these are k minus 1 plus n minus k squared. They stay massless, their propagator stays trivial. But on the other hand, all the n minus 1 minus the unbroken ones, they do get a non-trivial propagator. So they do get a non-trivial potential or mass. And this mass will take this form. I will write it here. So this again depends on space-time. Should be something like this. This is basically a 3-point function. This is like the exact same space-time dependence we found for SU2. We again get lambda, and then we get this simple sine square of pi s over k. Okay, so this is what we get. You can like modulo this space-time dependence, you can see that all these masses, so let me call this one big M square S, they all take value in the segment 0 lambda, and depending on the value of k, they populate it more and more densely as k gets larger. Okay, so the propagator of, so since the space-time dependence is exactly the same as it was for the rank 1 case, now the propagator of the massive modes will be exactly the same that it was for SU2. So this was, I called it T. Before it depended on lambda, now it will depend on lambda sine square pi s over k. So we will have more of them corresponding to all the like broken directions. Okay, so now that we know how many fields, we know how many like non-trivial, so this will take into account all the lambda dependence and leading order in large charge. So now we are ready to compute correlation functions. But before going to 3 and 4 point functions that I will discuss very, very briefly, I just wanted to make a comment on 2 point function, which are, as we mentioned before, 3-level exact, but still there is something funny that happens. So there was a paper by a relatively old result by Ellerman and Maeda. So in this paper, and actually a series of papers, they study extremal correlators in n equal to gauge theories in the large charge limit. In particular, you can consider, n equal 4 is a special case of this. And they study 2 point function. So what they do is much less trivial, but I'm going to restrict to n equal 4, so everything is 3-level exact. And they consider only rank 1 case. So in rank 1, they were able to write down a large charge GFT, and they used it to compute like 2 point functions exactly, well, at large charge. And they found some universal result that as n goes to infinity, they got a log of gamma n plus 1 plus alpha log n plus 1 over n, maybe order 1 and 1 over n corrections. So again, this is derived from some EFT that basically takes care of all massless degrees of freedom that you end up with on the Coulomb branch in this large charge regime. Okay, so this parameter alpha is given by the twice the A anomaly of the CFT, which is n equal 4 in our case, minus the A anomaly of the large charge EFT that describes this kind of correlation function. So again, this is supposed to be so this is somehow universal, so it works also for like n equal 2 or Douglas and so on. But in n equal 4, this is the simplest possible case. In this case, like any massless n equal 4 multiplet corresponds to 1/4, so contributes to 1/4. So in the case of SU2, what we get is like 2 square minus 1/4 in the CFT. And the EFT, you only have one massless mode, so this is just 1. Okay, so this is an old SU2 story. Now the comment I wanted to make is that in the SUN case, there is no EFT, well, as far as I know, no EFT has ever been written down at a rank higher than 1, but we can still formally play this game and check whether it is true or not. So if we consider SUN, this alpha would be twice the number of massless modes that you have in the CFT, which is just n square minus 1/4, and then the number of massless modes that you would get in the EFT, and they are simply the number of massless modes that correspond to the Xing pattern induced by these operators. So this is like k minus 1 plus n minus k squared. And it turns out that this formula is correct. You can verify it like numerically, or like you can compute a bunch of them analytically, and you can see that this formula is exactly correct. for basically all the n case we checked. So this is well, there is no EFT derivation of this because there is no EFT that, as far as I know, at higher rank. So this is a nice, if you want, prediction of some putative EFT that one could write down. Okay, this was for what I wanted to say for 2-point functions. Now, 3 and 4-point functions can be again computed using exactly the same formula we used for the SU2 case. So we evaluate the correlation functions of all the light operators in the vacuum, in the theta vacuum in which the gauge group is fixed, and finally we integrate of theta between 0 and 2 pi to get the full result. So again, since in the theta vacuum the gauge group is fixed, what you have to do is you take these operators, expand in modes, and consider all possible weak contractions, and the massless ones will contribute with like trivial things, and the massive ones will contribute with like all this t square that were there also in the SU2 case. This is for SUN now. And yeah, this is for SUN. It is formally the same as for SU2. The only difference is that now you have to use the correct propagators and all the massive ones. And each of these t square propagator will basically the sum of the lambda dependence. So just to give you a flavor on how this works, in the SU2 case, you can consider, for example, like the simplest 4-point function. This will be proportional to t square minus 1, actually. T square minus 1 in SU2. Now, this was coming from the only massive propagators that we got. In this case, we got many more of them. So the result will be basically taken into account by the sum over all the massive spectrum or broken direction. And each broken direction will contribute with one of those propagators. So with this, you can compute 2-point function, you can compute like Konishi 3-point functions. So for example, just to draw some picture, something that we computed is the so of course we computed like this kind of 4-point functions. And maybe a bit maybe more interesting is the Konishi 3-point function. So let me call this C, or how did I call it? So this is the, if you want, the OP coefficient of the Konishi, so the 3-point function of the Konishi with 2 of these heavy operators. And this is given you get some 3-level factors, and then some correction C1 of lambda. This, in the case of SU2, was computed already in the paper by Joao, Shota, and Ivan Wang, and they got something like this. This is for SU2, and you can compute it for different values of n, and you will get something like this. So you get a 0 here at some value lambda star that gets closer and closer to the origin. This, for example, n equal 3, n equal 4, and so on. Okay. So as I mentioned, I want to conclude with some simple comments of what happens if we take the limit and go into infinity. So I was mentioning before that we get these masses that roughly take this value here. So let me take k equal n now. because the idea is to send n to infinity. They take value in the interval 0 lambda, and for example, and you get a bunch of them for any values of n. What happens is you can convince yourself easily that as n goes to infinity, these masses will densely populate the interval 0 lambda. So, as I was mentioning, every time that you compute some correlation function, this is typically given as a sum over S by, and then you get all the, like, yes, yeah, I'm almost done. So you get the sum over the massive spectrum, that then you have all these correlators, like all these propagators. When n goes to infinity, this sum is simply substituted by an integral. So this is a nice feature because this is something that we somehow expect it should happen for large n theories. Because, for example, if you consider some, so if you, like there is this law in usual, for example, holographic correlators at large n, in which the heavy states are actually heavy, which at finite central charge, you would get a finite number of like things entering the OP, for example, but when C goes to infinity, like the number of things, the number of poles in the 2-point function get dense from Sakat, and sums should be replaced by integrals. So it's kind of nice that this feature is also appearing in this context. So maybe this is capturing some features of large n in general. Something also I want to conclude with is that if you take n goes to infinity, so just an indication that this limit is well defined, you get that this 0 converges to a stable point that I'm gonna call L bar, that is around 0.2, which is a funny thing, I don't know what it means. Okay, so just some comments to conclude. So something we don't really understand is why maximal trace behaves so differently. So this is a puzzle we have. And of course, like a very nice thing would be to find some kind of bulk interpretation of these objects, because like this is not really an holographic regime because the dimension is not scaling with large n, but is scaling with small n. So the dimension is the largest parameter in the game. But we can think of it as like, okay, delta is much larger than n squared. Maybe we still have some kind of bulk geometry that simplifies, that admits a limit like this. So for example, a nice thing we could play with, if we analyze the space-time dependence in detail of this kind of object, maybe we get some like feature of locality, I don't know. But anyway, can we say anything about bulk interpretations of these correlation functions? And then there is this funny feature of this 0 in the Konishi that we don't know what it means. So it means that like the Konishi is 3-level exact when we evaluate it at this finite value of the coupling, which like we don't know what it is. Okay, this is everything I wanted to say. Thank you.
So we already had answered, but there is still time for a few questions because we can break. Questions, comments, observations? Yes, over there, Marco.
Very simple question. So I didn't get why you cannot generalize to n squared. If I take another limit to gn squared fixed non-step gn, and I consider operator scaling goes like n squared, apparently I should proceed as you did. What am I missing here?
So like there is the most operatively way that I have to answer this question is that, as I mentioned, we are passing through localization. And when the dimension of the operator scale with n squared, the localization expression is more complicated and we don't have full control. So for example, something that you can do is, something that we used, So take this integrated correlator, compute it with localization, go to the large charge double scaling limit. You can evaluate, you can resum it completely. You can get an expression that, like, you know how every coefficient behaves. So you can write the else coefficient of the series, and you can even resum it. If delta scales with n square, we don't know how to do this.
But in principle, I mean, now because we found the shortcut, but in principle, you can, with some little bit of effort, find this omega just by directly without bypassing the localization.
Yes. If one finds out, but I think it's very hard because, like, you should, even for n infinity, how do you open up the matrices? I don't even know, because, but yeah, in principle there should be a way.
Please.
Can I ask something about this bulk description? Isn't it just the two-point function of two-heavy operator, which is like some kind of
Banana.
yeah, if you think about some string theory, for instance, the description of that is like, and then you have some light field, which perhaps, I mean, why am I thinking about?
No, I think it could be just that.
This has been studied.
Yeah. We didn't check in details. But it could be that.
Yeah.
But sorry, do you mean these like banana things with like all these probe? Okay. Okay.
Like a 2.5, you take a string state, and you
Yeah.
function semiclassical, and then you insert the light state. And this gives, for instance, a two-point function similar or higher, similar to what we discussed, like too heavy, which creates this, so there is no back reaction when you have the light field. This has been studied around 2010 or something.
Mm-hmm.
People did that also using integrability.
Yeah, but also they do some area calculability, semiclassical computation.
You can do it several ways, but
yeah,
this is, for instance,
worship computation.
I'm not sure if I'm not
No, I'm
understanding something.
it.
But my it's not very hard to compute. You take a string.
Yeah.
One function.
But these operators are not as heavy as the central charge, right? So they are like the stringy operator.
Yeah.
So I think he had in mind more heavy operator, right?
Yeah.
So if you take back or like I don't know some graviton.
Yeah, I think you can make.
But again, I think giant ranking is still the dimension order n, not order n square.
And this is even larger than, I don't know, I'm not very familiar. So what I had in mind is that, so this is a rough BPS, this should be some LLM somehow, but LLM delta is n square, so it should be some, so what I had in mind, but it could be that like there is a simpler answer. What I had in mind is, okay, maybe some LLM geometry in some large charge limit in which you decouple delta.
I guess the difference is whether you can you want to see this operator as deforming the background, or as Agnese was suggesting, as some object, right? Some string state or some deep brain in fixed background.
Yes.
I think this type is lighter operator, where the dimension does not scale as the central charge, but scale to some fractional power of the central charge.
I think it's mostly a question of whether you're walking in flat space like you did here, or you're walking on a cylinder. Because here is walking in flat space, so whatever you're doing is at some local deformation. So even with these bananas, they are considering things that scale like some power of C is a large power of C.
Yes, I think they can.
So you have to have like very far away from the operator, you can't really see the deformation of the space if you're walking on flat space side. But you could as well just walk on the cylinder, just like you did, and then I think it's just describing a different background.
The describing a? What did you say? It's describing a?
Different background. I mean, if you think of the state you're walking with as the state that's created by acting with this heavy O and that far past and like heavy O bar in far future, just walking on a different background.
Yeah, I don't know. To me, like the most weird, the weird. So like it's just that I'm not aware of like backgrounds that describe delta that is much larger than n square. So this is why we didn't. But okay, maybe it's simple. It would be nice if it was simple. It would be fun.
Comments, questions. So it's time to thank Cristoforo again. Let's try to